Okay, let's have a look at the second lesson of chapter 3 curves, chapter 3 curve sketching. Today we're going to have a look at concavity, point of inflection, and the second derivative test. Okay, first of all, let's have a look at today's learning goals. After this lesson, you are expected to be able to understand the concept of concavity and point of inflection. Determine the interval of concavity and point of inflection using second derivatives. Then determine local extrema using both first and second derivative test. Okay, first of all, let's have a look at the concept of concavity and point of inflection. Okay, remember last time we have learned turning points and critical points, right? Today we introduced a new concept, new type of point, which is called point of inflection or inflection points. Okay, first of all, the graph of a function fx is called concave up on the interval a to b if all the tangents on the interval are below the curve, or if the second derivative of x is greater than 0 in this interval. Whereas the graph of a function fx is called concave down on the interval a to b if all the tangents on the interval are above the curve, or if the second derivative of fx is strictly less than 0 in this interval. And a point at which the graph changes from being concave up to concave down, or vice versa, is called a point of inflection. If the second derivative x equals 0 and second derivative of fx changes sign at a, then we say there is a point of inflection at a. These concepts are illustrated in the two graphs below. So as you can see here, in the left diagram, the left side of this graph here, all of the tangents on this interval are below the curve. Sorry, above the curve, right? According to the definition, we say this graph is concave down in this interval. And from this point all the way to cos infinity in this interval, we can say that all of the tangents on the interval that is below this curve, right? Therefore, this interval is an interval of concave up. And at this point, the curve changes from concave down to concave up. Therefore, this point is called point of inflection. And there is another example shown here on the right. So basically, this concept tells us how to find the point of inflection. We need to check the second derivative and then check if the second derivative changes sign at this point, right? If it does change sign, then this point is called point of inflection. And any interval, if the second derivative is greater than 0, then this interval is concave up. And if on any interval, the second derivative is less than 0, then this interval is called concave down. So basically describes the shape of the function, right? That relates to the second derivative. So similar to the monotonicity, which we have learned in the previous lesson, the concavity is another important property of the function. It describes the shape of the function. Understand? Whereas the monotonicity describes the trend of this function. Okay. All right, so let's have a look at some examples to illustrate this concept. First of all, let's consider this question. For the function fx equals x to the power 4 minus 6x squared minus 5, find the points of inflection and the intervals of concavity. Okay, I'll give you 5 minutes to think about this question by yourself. How do we find points of inflection? Okay, have you finished? Let's have a look at the solution. Okay, first of all, in order to find the points of inflection, remember we need to check its second derivative, right? So we can find the first and second derivative of this function. First derivative of fx equals 4x cubed minus 12x, right? Then based on that, we find the second derivative, which is 12x squared minus 12, right? Then in order to find the point of inflection, we first let the second derivative be 0. Note that the second derivative is 12x squared minus 12, right? So this is actually a quadratic function. We can analyze this graph to find any point that makes this function be 0. And any interval makes this second derivative either be positive or negative. The graph of the second derivative is drawn on the bottom left. Okay, first of all, if the second derivative is 0, we solve for x and get x is either -1 or x is +1. Then we find the value of the function at these 2 points. When x equals -1, fx is -10. And when x is +1, fx is -10 as well. Next, let's analyze its concavity in different intervals. So the 2 points x equals -1 and x equals +1 really divides the second derivative to 3 intervals, right? As shown here on the bottom left. When x is less than -1, you can see the sign of the second derivative is always positive, right? And when x equals -1, the second derivative is 0. Next, when x is between -1 and +1, the sign of second derivative of fx is always negative. And when x equals 1, the sign of the second derivative is 0. And when x is greater than 1, the sign of the second derivative is positive. Therefore, we have the first row as shown here in this table. Then, according to the point of inflection and concave up and down, according to this table, we have if on some interval, the second derivative is always positive, then we say this interval is interval of concave up. Then in the next interval, x is between -1 and 1. The second derivative is always negative, right? Therefore, we say this interval is called an interval of concave down. And in the next interval, when x is greater than 1, the second derivative is always positive. And according to the definition, we say this is an interval of concave up. Then let's check if the 2 points are the points of inflection. So in order to be a point of inflection, first of all, at this point, the second derivative must be 0, right? The second condition is there is a change of the second derivative sign at this point. Now let's check if this is the true. So at this point, the second derivative is 0, right? And before x equals -1, the sign of the second derivative is positive. After that, the sign is negative. The second derivative does change sign at this point, right? Therefore, x equals -1, or the point -1, -10 is a point of inflection. Then let's check the other point when x equals +1. Before x equals +1, the sign is negative. Second derivative, the sign is negative. And after x equals 1, the sign of the second derivative is positive. Again, the second derivative changes sign at x equals 1, right? Therefore, we say when x equals 1, or at the point 1, -10, this point is called a point of inflection, right? You understand? So this is how we can find the point of inflection, or any interval that is concave up or concave down. Understand? Okay. Any questions? If not, let's see another example. So this time we have a function fx equals -1 over x plus 2. Can you find the intervals of concavity and any points of inflection, if any? Okay, again, I'll give you 5 minutes to think about this question by yourself first. All right, let's have a look at the solution together. Okay, first of all, in order to find the concavity, intervals of concavity and the point of inflection, that involves a second derivative, right? So first of all, we find second derivative of this function. First, differentiate this function in order to find this first derivative. First derivative of fx equals, so note that this function is a composite function. The outer function is a power function. Inner function is a polynomial function, right? So first derivative equals x plus 2 to the power of -2 times 1 times, well, actually, there should be, okay, x plus 2 to the power of -2 times 1, which is x plus 2 to the power of -2, right? Then based on the first derivative, we differentiate it again to get this second derivative, which equals -2 over x plus 2 to the power of 3. Any questions here? Oh, okay. Then in order to find its points of inflection, we need to let f a second derivative of fx equals 0, right? As you can see here, there is no solution to this equation, right? That means no matter what x is, the second derivative cannot be 0. Therefore, actually, there's no point of inflection. Then, in order to find the intervals of concavity, that means concave up or down. We let the second derivative be greater than 0, which means -2 over x plus 3 cubed greater than 0. This is equivalent to x plus 2 cubed must be smaller than 0, right? This gives us x plus 2 must be smaller than 0. Therefore, x must be smaller than -2. Understand? Next, well, if you find x is smaller than 2, makes the second derivative be greater than 0. That means that interval is an interval of concave up, right? Next, we can let the second derivative be less than 0 and find that x is actually greater than -2, right? Therefore, we know when x is greater than -2, that interval is called interval of concave down, right? So now we can make the conclusion. First of all, there is no point of inflection. Second, the interval of concave down is from -infinity to -2, open interval. Third, the interval of concave up is from -2 to positive infinity. Any questions? Okay, if you don't have any questions, let's have a look at the next concept, which is to determine the local extrema using both first and second derivative tests. So basically, in our previous lesson, we have already studied, if you want to check the local extrema, first of all, you need to find its first derivative, right? Then you need to check whether the first derivative changes sign before or after that point, right? So in this lesson, we are going to learn a new method to check the local extrema using both first and second derivative tests. Okay, first of all, we have the following two statements. Let's have a look at this statement here. If the first derivative at some point x equals a equals 0, and also the second derivative at this point x equals a is greater than 0, then fx is concave up. There is a local minimum at x at a f a. You see why? Because first of all, if the first derivative is 0, then this function is either the instantaneous rate of change of this function is 0, right? So this function is either this way, looked like this, or sometimes this or this at this point. If the first derivative is 0, the instantaneous rate of change of this function at this point is 0. Next, we check the second derivative. If the second derivative is greater than 0, this means this function is concave up at this point, right? So the only possibility is this one. Then if you know the first derivative is 0 and second derivative is greater than 0, we know that point should be the local minimum of that function, right? You understand? So in the future, in order to facilitate our discussion to find the local extrema, you can find its first derivative, let the first derivative be 0, and check its second derivative, right? If the first derivative is 0 and the second derivative is positive, then we can decide that point should be a local minimum. And similarly, if the first derivative is 0, and then we check the second derivative, if we found that the second derivative is less than 0, then that corresponds to the graph here, right? Then in that case, that critical point is a local maximum. Understand? So that really gives us another method to check the local extrema, whether it's local minimum or local maximum. Basically, you need to check the first derivative, let it be 0, and check the second derivative. Understand? Okay, so you might want to say, so what will happen if the first derivative is 0 and the second derivative is also 0? Well, in that case, that's a special case, which is included here. If the first derivative is 0 and the second derivative is also 0, in this case, usually we can't determine directly. In this case, we need to check the first derivative of fx changes sign from x is smaller than a to x is greater than a, or in the vicinity of a, as what we have done in our previous class. You need to check the sign of the first derivative before and after this point, okay? In order to determine if this point, AFA, is really a local maximum or minimum or neither, okay? Specifically speaking, if the first derivative of fx changes sign from positive to negative, then this point AFA is called the local maximum. Then if the first derivative of fx changes sign from negative to positive, then this point AFA is called a local minimum. Otherwise, this point AFA is neither local maximum or local minimum. You understand? So if you find the second derivative is also 0, then you need to go back to the method we have discussed in our previous lesson. Okay, check the sign of the first derivative before and after that point. Okay, any questions? Any questions? Okay, if not, let's have a look at an example to illustrate how we can use this method to find its logo extrema. Okay, let's consider this question here. For each function below, find the critical points. Then determine if each critical point is either local minimum or local maximum or neither. Okay, do you still remember the concept of critical points? Any point that makes the first derivative be 0 or not exist, right? Okay, I'll give you 5 minutes to have a look at these two questions using the method we have just learned, okay? Checking both the first and the second derivative of the function. Okay, let's have a look at the solution of these two questions. Okay, first question, let's find this first derivative. First derivative, so note both of the functions are polynomial functions, right? We have already learned how to differentiate them. First derivative of fx is 3x squared minus 6x. Then differentiate again. Second derivative is 6x minus 6. So we can let the first derivative be 0 to find any critical points. That gives us two solutions. X is either 0 or x is 2, right? Then in order to check and categorize the types of the critical points, we check its second derivative. So at x equals 0, the second derivative is 0 minus 6, which is less than 0, right? Therefore, we know, well, before we do that, you need to also calculate the values or the image of the function at x equals 0 or x equals 2, right? So also note that f0 is 2, f2 is negative 2. And the second derivative of x equals 0 is less than 0. Therefore, we know the point 0, 2 is a local maximum, right? Because at this point, the first derivative is 0, second derivative is less than 0. Therefore, this point is a local maximum. Okay, at the next critical points, when x equals 2, it's very easy to see that second derivative is greater than 0, right? Therefore, at this point, the first derivative is 0, the second derivative is greater than 0. Then we say this point 2, negative 2 is a local minimum. Understand? This is a quick way, shortcut to find this local minimum or local maximum. Okay, second question, question B. First derivative f prime x is 4x cubed, right? Second derivative is 12x squared. Then again, we can let the first derivative be 0. Then we solve in terms of x, that gives x equals 0, right? Then we find the image of this function at x equals 0. That gives us f0 equals 0. Therefore, we say 0, 0 is a critical point. But this time, if you check the second derivative, you can see that the second derivative is also 0, right? So if the first derivative is 0 and second derivative is also 0, we cannot immediately decide whether this point is a local minimum or local maximum, right? So we can refer to the method we have learned yesterday, in which you need to check the first derivative before and after that point, right? So note that the first derivative is 4x cubed. For x is smaller than 0, the first derivative must be smaller than 0, right? And for x is greater than 0, the first derivative is greater than 0. That means the first derivative changes sign from negative to positive before and after 0, 0, right? That means 0, 0 must be a local minimum. You understand? If the second derivative test does not pass, we refer to the method we have learned yesterday. Check the sign of the first derivative before and after that point. Any questions? Okay, if you have no questions, let's consider another example. Can you sketch a graph of a function that satisfies each set of conditions? Question A, the second derivative equals -2 for all x. First derivative at x equals -3 is 0. And the image of this function at x equals 3 is +9. In the second question, the second derivative is less than 0 when x is less than -1. The second derivative is greater than 0 when x is greater than -1. And the first derivative at x equals -3 is 0. Also, the first derivative at x equals 1 is 0. Apparently, there might be unlimited number of functions like this, right? So can you find one that satisfy each set of conditions? Okay, I'll give you 5 minutes to think about this question. Okay, have you finished? Can you find one? Okay, let's have a look at the first. Okay, if the second derivative for all x is a negative number, that means the whole domain is a interval of concave up, concave down, right? So basically that function could have a graph like this. Then we know the first derivative at x equals 3 is 0. So that means x equals 3 is probably a critical value, right? So we can let this point be -3. First derivative is 0 means the instantaneous rate of change here is 0, right? So we can let this point be -3. Then also we know f -3 is 9. So can let the coordinates of this point is -3, 9. So that's a possible graph of such a function. So next, note here the second derivative is less than 0, 1 x equals is less than -1, and 1 x is greater than -1. The second derivative is greater than 0. So that means x equals -1 is a boundary, which makes this function changes from concave down, something like this, to concave up, right? So we can say this x coordinate is x equals -1. So this point is -1. This point is called the inflection point. And also we know f, the first derivative at x equals -3 is 0. That means when x equals -3, is instantaneous rate of change is 0. So that's the local extrema point, which is probably here, right? Again, there might be unlimited number of solutions. We're only talking about one possibility. So this point here is x equals -3. And also we have the first derivative at x equals 1 is also 0. So that means the sketch of the graph here is probably not correct, right? So this should be something like this. There exists a local extrema here because at x equals +1, the instantaneous rate of change is also 0. So that's one possibility of the curve of this function, right? Okay, so now let's have a look at the proper writing of the solutions. Okay, I'll give you some time to have a look at the solution. Any questions, just let me know, okay? Again, there might be an unlimited number of solutions. The graphs shown here are just one of the many possible solutions. For example, if these graphs were translated up by k units, k is a real number, the new graph would also satisfy the conditions, since there is no specific points were given, right? Okay, if you don't have any questions, let's make a summary of today's lesson. So today we have learned concept of concavity and point of inflection. and also the first derivative and second derivative tests. So now you should be able to first understand the concept of concavity and point of inflection. Then determine the interval of concavity and point of inflection using the second derivatives. And last, determine local extrema using both first and second derivatives test. All right, if you don't have any questions, class dismissed for today. Remember to complete your homework on Google Classroom and submit that on time, okay?